All right, so the last part of this section on equilibrium is going to focus on how we can calculate equilibrium constants, or if you are given equilibrium constants, how we can find concentrations or partial pressures of the components. We're going to be using what's known as an ICE table to help us to do this, because sometimes you may be given equilibrium concentrations or partial pressures, which are pretty straightforward as to how to calculate K, but we can also use initial concentrations or partial pressures to determine what the equilibrium constant value will be, because the relationship between the reactants and products can be examined stoichiometrically, and we can use Q to determine the shift in the direction of the reaction, whether it will move in the forward direction or whether it will move in the reverse direction. And so we're going to get a chance to practice all of those in this section. So here we have a reaction where nitrogen and chlorine are making nitrogen trichloride, and we are told this mixture is at equilibrium. So all three concentrations that we are given are for the equilibrium concentrations of these gases, and we want to calculate what K is. So to calculate K, we need to write an expression for what K is equal to in terms of these reactants and products, which would be the concentration of NCl3 squared over the concentration of N2 and Cl2 cubed. Again, those exponents are based on their coefficients and the balanced equation, products always written over reactants. We would then substitute in what we know for concentrations for those three components. NCl3, would be 1.9 times 10 to the negative first. N2 would be 1.4 times 10 to the negative third. And chlorine would be 4.3 times 10 to the negative fourth cubed. We do our math, multiply, divide, all of those have 2 sig figs. So when I do my calculation, I get that this is a pretty large K. So it definitely favors the nitrogen trichloride being formed, the forward reaction, 3.2 times 10 to the 11th. And again, this is specific for the temperature that what this reaction has been performed at, 303 Kelvin. Here we're given some partial pressures for forming ammonia from nitrogen and hydrogen. We're going to calculate Kp. Since we have pressures, we would write our Kp expression in terms of partial pressures, ammonia squared being the product, nitrogen and hydrogen cubed being the reactants, products over reactants, coefficients giving us our exponents. Substitute in our quantities. 3.1 times 10 to the negative second for ammonia, 8.5 times 10 to the negative first for nitrogen, and 3.1 times 10 to the negative third for hydrogen. When we get through doing all that math, 2 sig figs, because of all the partial pressures had 2 sig figs, this K is still favoring the products, but not to the extent it was in the prior question. 3.8 times 10 to the fourth. And again, this is for the temperature of 328 Kelvin. So now we're going to get into some that are not as straightforward. You have a sample of sulfur that was placed in an otherwise empty rigid container at 1325 Kelvin, initially at 1 atmosphere of pressure, and it decomposes to S2. And in the following equation, at equilibrium, we are told S8 has a partial pressure of 0.25. And we want to calculate what K is when the reaction is at equilibrium for 1325 Kelvin. So if we take that reaction and we write our K expression using partial pressures, because that's what we were asked to calculate it for, Kp, S2 would be raised to the fourth over S8, again based on the stoichiometry. So now we're going to get into that ICE chart that I talked to you about briefly before. The ICE chart stands for initial, change, and equilibrium. Initially, we are told we have 1 atmosphere of S8 present. If you aren't given information about any of the other components, you are more than welcome and absolutely should assume that they are at 0. We're told at equilibrium, S8 was at a partial pressure of 0.25. Well, that meant it decreased, and it decreased by 0.75 atmospheres, if that was the only way we were going to get it from 1 to 0.25. So if that change is equal to our X, sulfur S2's increase is going to be 4 times that, because if the right side decreased, if the reactants decreased in terms of partial pressures, the products had to increase to balance out that. So when I solve for what S2's equilibrium pressure would be, 0 plus 4x, at equilibrium it would just be 4 times whatever x is. Well, we know what x is 0.75. So at equilibrium, 4 times 0.75 would give me the partial pressure of S2, which would be 3 atmospheres. I substitute those equilibrium partial pressures into my equilibrium expression. I solve the math. They both have 2 sig figs, so my Kp is 320. So again, if you're given initial values and an equilibrium, we can use that to determine by what amount they change stoichiometrically, and based on the relationship between the reactants and products, we can determine any other equilibrium quantities, as long as we have an initial and an equilibrium partial pressure or concentration for one of the components in our reaction. Here we have 4 moles of ammonia that's being introduced into a 2-liter container, and the ammonia partially dissociates. You've got that equation. At equilibrium, you have 2 moles of ammonia remaining. So we have an initial amount of ammonia and we have an equilibrium amount of ammonia. Start with writing your equilibrium expression, products over reactants, because we were breaking down ammonia. Ammonia will be a reactant, nitrogen and hydrogen will be our products. We set up our ice chart. Molarity is what we need to have inside of the bracket. So we take the 4 moles of ammonia and divide it by 2 liters to get 2 molar. And we do the same thing for equilibrium, which would be 1 molar. We were not given any information about nitrogen or hydrogen, so they are starting out initially at 0 molar. Because we have no products, we have to shift towards the forward reaction. It would be a Q of 0. So we would decrease our reactants. We can tell that by the equilibrium value. We're going to decrease them by 2x. Nitrogen is going to increase by x, and hydrogen is going to increase by 3x. If we solve the math through, I believe you're going to get that your x, the initial minus your change, will always equal your equilibrium. That will give you a change of 0.5. And so if I take 0.5 away, from that, if I take 0.5 times 2, that would give me my 1. And then 2 minus 1 would give me my 1 molar. So I guess I should be more clear. It's the initial plus the change, since we're including the negative sign as part of the change, that gives you your equilibrium values. So if you start at 0 and your x is 0.5, nitrogens would also have to be 0.5. Hydrogens, however, would be 3 times that, 1.5. So I substitute those quantities into my equilibrium expression, 0.5 times 1.5 cubed over 1 squared, and that gives me a K of 1.7. So we've seen how to do equilibrium problems when you are just given the equilibrium concentrations, or when you're given an initial and an equilibrium concentration. You won't always necessarily be given equilibrium concentrations, but because of the stoichiometric ratios, we can solve for what x is and then determine what our equilibrium concentrations might be. So if you are solving a problem and you don't have a balanced equation, you definitely need to get that started first. You're going to write your equilibrium expression based on that equation, identify whatever initial concentrations you're provided with, set up your table or partial pressures, define what equilibrium will be in terms of x, if nothing else, and then put those into your equilibrium expression and solve for what x is. So when you're given a situation like this, typically you are given your equilibrium constant. If it is a more complex algebraic equation, you may have to use your quadratic formula, which I know will bring joy to your hearts, or you can graph it, and we'll talk about that tomorrow. And then you can actually substitute those concentrations in by calculating K, just to verify what you got. So here we have hydrogen and iodine making 2 HI, hydrogen iodide gas molecules. You're given the Kp is 45.9. At equilibrium, we are told we have 4 atmospheres of HI and 0.2 atmospheres of hydrogen. And we want to know the partial pressure of iodine. So this is starting out a little bit more simplistic because we have equilibrium partial pressures for 2 of the 3. And we want to find the third one, and we know what Kp is. We have a balanced equation. We can write our K expression from that equation, partial pressure of H high squared over the partial pressure of hydrogen times the partial pressure of iodine. We don't have to necessarily set up an ice chart for this because we don't have any initial values. We only have equilibrium values. We know what our K is, we know what our pressure of HI is, and we know what our pressure of hydrogen is. We should be able to use those pieces of information to find the pressure of iodine. And if I go through and do the math, all 3 of those values have 3 sig figs. The partial pressure with respect to iodine for this equilibrium mixture at 763 Kelvin would be 1.74 atmospheres. I do think this one is going to involve initial quantities. We have a K of 0.09 for hot water, steam and dichlorine monoxide forming hypochlorous acid in the form of a gas. We are given the concentrations of these species at equilibrium when you have a gram of water and 2 grams of dichlorine monoxide mixed in a 1 liter container. So we only have initial amounts, and we want to figure out what we have at equilibrium for all 3 components, the 2 reactants and the 1 product. Our equation is balanced, so we can write our K expression, and again, it's a K as opposed to a Kp based on the products over the reactants. We'll set up our ice chart. We need to have molarities, so we have to convert those grams into moles and then divide them by the volume of the container. So 1 gram divided by 18.02, the molar mass of water, would give me my moles, and then I divide that by 1 liter. I got that to be 0.055 molar. I would do the same thing with the grams of dichlorine monoxide. I'm doing this really quick in my head. I want to say that's going to be 86.90 is the molar mass. That would get divided by 1 liter, and that gave me a molarity of 0.023. I had no HOCl present initially, so it will have a concentration of 0. I have no products, and my K is not 0, so I have to shift. My Q would be 0 because products over reactants, if you have nothing in the numerator, your Q is going to be 0. Your reaction is going to have to shift towards the products in order to reach equilibrium, which means water is going to go down, dichlorine monoxide is going to go down, and the HOCls are going to increase by a factor of 2 times X. So at equilibrium, if I add the initial and changes together, I get what water's equilibrium concentration, dichlorine monoxide's equilibrium concentration, and HOCl's equilibrium concentrations are. I can substitute all of those into my equilibrium expression. I do have the value for K, 0.09. So if I put those quantities into my equilibrium expression, accounting for the exponents, so the 2x would need to get squared. This is why I said that you very well may want to have a calculator that can graph today available during class, because this would not be the most fun to have to solve for x in terms of. But if you set up your graph so that y1 would be 0.090 and y2 would be this equilibrium expression, the right side of your equation as y2. Make sure that your boundaries are pretty large. I think I usually go with negative 100 and 100 and plus 100 and minus 100 for my x and my y-axis. So I make sure that it will graph the intersections. But you can go through and solve this through algebraically, good old school. And when you go through and do the math, if you do it on your calculator, your x may be slightly different than mine, but it should be pretty close to 4.5 times 10 to the negative third. I would then plug that x in to my equilibrium concentrations for water, dichlorine monoxide, and HOCl. And that's when I got 0.051, 0.019, and 9 times 10 to the negative third. This K was not super big, nor was it super small, 9 times 10 to the negative second. When we start to get into Ks that are super small, when we're having very few products being generated, we're going to be able to make an assumption where you're not going to have to put these in your calculator. I know you're going to want to. I'm not going to fight you on it, but we're going to see in class why it's not significantly going to change your answer. And we basically use what's called a 5% rule, that if omitting the X is going to result in a change in concentration that is a value of X that is less than 5% of the initial concentrations that you are provided with, then you are making a reasonable assumption and we don't have to get so caught up in all the math. And so we see that here in this example. We have dinitrogen tetroxide breaking down into nitrogen dioxide. The K is 4 times 10 to the negative 7th. So primarily it's staying as N2O4. Only a very small fraction is being converted to NO2. We do have a balanced equation, and we're taking 1 mole of N2O4, we're placing it in a 10-liter vessel, and we want to know what the concentrations are of these two components when equilibrium is established. So I've got my balanced equation, I can write my K expression, I can set up my ice chart. Again, molarity divided by volume gives, or sorry, moles divided by volume gives me molarity. So 0.1 for the N2O4. I had no information about NO2. I know because I have no products, the reaction is going to have to shift in that direction, which means N2O4 is going to decrease and NO2 is going to increase by a factor of 2x. This would be one, and by what I'm saying about it being reasonable to make the assumption, it's pretty reasonable to assume that that 0.1 minus x, that whatever the difference is between 0.1 and x, it's not going to appreciably change the concentration of N2O4. Typically, if the initial concentrations are 2 or 3 factors of 10 greater than your value for K, you're pretty safe in making the assumption that you can omit the x. So that's what you're going to see down here on my setup. Now, I know for those of you that are freaking out right now because what, you're dropping an X, you can put that into your calculator and you can do the graphing like we did on the previous problem. But I suspect when it's all said and done, you're going to get a value that is pretty close to mine, 1 times 10 to the negative 4th. Now, if that is your value of X, 0.0001 is what you're wanting to take away from 0.10. In terms of sig figs, that is not going to change the concentration of N2O4. It is, however, going to cause a slight increase in the NO2, which is what we need to have take place for us to have some reactants and some products at equilibrium. We can again verify that our assumption was a reasonable assumption to make by using a 5% rule. So there's just me substituting in the value of X for N2O4 and NO2's concentrations at equilibrium. I take the value of my X, how much the concentration of N2O4 should have changed by, and I divide it by its initial concentration. And if that is within 5%, that's basically telling me what percentage of it dissociated, broke apart, or was able to form NO2. And if that percentage is under 5%, we were safe assuming that 0.1 minus x did not need to be included in our calculation. Hope that helps, and please feel free to reach out if you have any questions.